Before we get into audio, it's important to understand what audio is exactly. We'll start off by talking about what sound is. Sound is a vibration through a medium or a material. It can be any material: wood, metal, water, or air. Generally speaking, when we talk about sound, we're talking about fluctuating waves of high and low air pressure called acoustical energy. Imagine an object falling into water. When the object hits the surface of the water, it forces it downward. The water then rebounds upwards. Each downward movement is followed by an upward movement. A very similar thing happens when sound travels through the air. When you hear a sound, you are really hearing the vibrations in the air caused by the sound source. The sound wave that reaches your ear is a result of energy being transferred from one particle to another. Unlike water, which ripples out in two directions, sound ripples outward in three directions, creating a sphere of acoustical energy. As the sound ripples outward from the source, it's moving more and more particles with the same amount of energy, and eventually that energy will be depleted. So how do audiophiles actually work? Everything starts with a vibration. Sound is created through vibrations called sound waves. Normal sound waves are actually tiny vibrations in the air. The vibrations travel through the air and into our eardrums. The eardrums in turn vibrate, decoding these sound waves into different types of vibrations that are received by the inner ear. The inner ear is connected to our auditory nerve, which transmits the sounds to our brain. Bone conduction bypasses the eardrums. In bone conduction listening, the bone conduction devices, things like headphones, perform the role of your eardrums. These devices decode sound waves and convert them into vibrations that can be received directly by the cochlea, so the eardrum is never involved. The sound reaches our ears as vibrations through the bones or skull and skin. Sound waves can be analyzed through a visual representation called a waveform. Anytime you edit sound or look at it on a timeline when editing in a digital application, you will likely be provided with a waveform that gives you the visual information about what is happening in the sound file. To understand what is happening in a waveform, let's look at wavelength, amplitude, and velocity. Wavelength is the distance between one crest and the next crest in a sound wave. It basically describes one full cycle of the waveform. Amplitude is the measure of positive or negative changes in atmospheric pressure caused by sound waves. These can be measured in an amount of force applied over an area. For instance, striking percussion harder creates a louder sound. Low amplitude sounds are quiet, while high amplitude sounds are loud. Think of an amplifier that is used to increase the volume of a musical instrument. It increases the intensity of sound using energy to increase the oscillations in electrical currents. Frequency is the measure of complete wavelength cycles in seconds. We call this CPS, or cycles per second. The name of this unit of measure is more commonly called hertz, which is named after a scientist who discovered frequency. It's a measure of time. The frequency of a sound determines the pitch and the sensation of how high or low a sound is. Lower frequency sound waves have longer wavelengths and lower pitch. Higher frequency sound waves have shorter wavelengths and higher pitch. The frequency range in which humans can hear is 20 Hz to 20,000 Hz, and this is called the audible range, or audible spectrum. Velocity is the speed and direction of a sound wave. Sound waves travel at different speeds through different mediums. Through the air, sound travels at 344 meters per second. Generally speaking, the denser the medium, the faster sound travels through it. To find the velocity of a wave, we can multiply frequency by wavelength. Notice how in this example, both have the same amount of time duration on the timeline. It's 1 second. The 4 Hz wave has 4 wavelengths per second, while the 9 Hz wave has 9 wavelengths per second. As you can see, the length of the waveform and the amplitude are going to change based on the frequency. Before we get too far along, let's talk about an audio file format and what it actually is. When we record audio in an analog format, like on a vinyl record or a roll of tape, the original audio waveform is stored directly on the medium. When we record audio on a digital format, like an MP3 or an audio file on a CD, the original signal is sampled, it's digitized and stored as binary code, which are ones and zeros. When a computer scans the code, it recreates the original audio signal. Some formats use data compression to reduce the size of the file. We'll talk more about that later. Audio resolution is determined by the sample rate and the bit depth of the digital audio recording. Sample rate is the number of samples of audio taken per second and controls the frequency response of a recording. When capturing digital audio, your interface takes thousands of snapshots of each waveform and plays them back in order to sound like one cohesive recording. It's kind of like how a video appears to be moving, even though it's just a series of still images, like a flipbook. Think of sample rate as an individual drawings in your audio flipbook. Each sample represents one small frame of the big picture. Using a higher sample rate will result in more samples. Put simply, it's how many samples or snapshots of the original signal the computer takes in the course of a single second, and this is described in kilohertz. A common sample rate that you will be using is 44 kilohertz. This extends just beyond the human hearing range and ensures that you can hear every detail in the recording. Bit depth is a measurement of how much data can be stored in each sample. This controls the dynamic range of the recording. It determines the amount of possible amplitude values we can record for each sample. If your sample is set to record at 24-bit, then it can take snapshots of the incoming audio with more accuracy. It's similar to the idea of megapixels in your camera. Bit depth in digital audio is one of the settings that affects the recording's overall resolution. In technical terms, it's the actual number of bits, binary digits, in each sample. If sample rate is the number of still frames or images in the flipbook, you can think of bit depth as the size of the notebook that you're actually drawing in. It dictates how much space you have to capture the recording. Bit depth and sample rate work together to determine the resolution of digital audio. While sample rate corresponds with the frequency content of a recording, bit depth is responsible for the dynamic range. The higher the bit depth, the higher the detail in your audio. You can kind of think of the bit depth as resolution in your camera. In summary, sample rate is the number of audio samples recorded per unit of time, and bit depth measures how precisely the samples were encoded. Having this overview of how sound and audio work will be helpful as we get into adding sound into our projects.